What if I told you that the entire universe runs on a really, really strict accounting system? That's basically the whole idea behind thermodynamics. It's not about scary formulas. It's about how engineers track energy and matter to predict and, literally build the world around us.
So let's start with a little puzzle. Think about a giant jet engine, the refrigerator humming away in your kitchen, and a massive power plant. What could they possibly have in common?
The answer isn't some physical part or a special material. It's that they all have to play by the exact same set of unbreakable rules. They all have to balance their books, so to speak, when it comes to mass and energy.
And that idea brings us to our first big concept, what we're calling the ultimate accounting rule. It's the most basic idea in all of thermodynamics, and honestly, it's something you already get.
It's the law of conservation of mass. And put simply, it just means you can't create matter out of thin air, and you can't make it just disappear. For anything an engineer is looking at, whatever mass goes in has to either come out or it has to stay inside, piling up. Nothing just vanishes.
I love this quote from the source material because it just makes it so clear. If you can balance your checkbook, you should have no difficulty applying the conservation of mass principle. It really is that simple. It's all about tracking what comes in and what goes out.
And that breaks down to a super simple equation. Mass in minus mass out equals the change in mass inside, right? Your deposits minus your withdrawals, that equals the change in your bank account. It's the exact same logic.
Okay, so how do engineers take that simple idea and apply it to something wild, like air screaming through an engine? Well, they use this brilliant little mental tool. Let's call it the engineer's magic box.
Now, the technical term for this box is a control volume. It's not a real thing. It's just an imaginary boundary that an engineer draws around whatever they're interested in. Could be a section of pipe, a whole turbine, whatever. It just lets them keep a close eye on everything crossing that line.
And using this box, we can talk about two different situations. First, there's steady flow. That's when the amount of stuff inside the box stays constant. Think of a garden hose that's turned all the way on. The water coming in equals the water going out. Then you've got unsteady flow. That's when the amount of stuff changes. Like when you're filling up a tire, air is going in, but nothing's coming out. So the mass inside the tire just keeps going up.
All right, so we've got our mass checkbook balanced. Now for the really fun part, energy. Because when we start dealing with stuff that's moving, flowing fluids, there's this fascinating kind of hidden turn on the energy balance sheet that we absolutely have to account for.
So, the total energy of a fluid has some parts you'd expect. You've got its internal energy, which is all the microscopic jiggling of its molecules. You've got kinetic energy from its overall motion and potential energy from its height. But when that fluid crosses the boundary of our control volume, there's something else. What is it?
That missing piece is called flow work. It's the energy it takes to physically shove the fluid into or out of our imaginary box. You can almost picture it like a tiny invisible piston that's doing work to push a chunk of fluid across that line. It's a type of energy that only shows up because the fluid is flowing.
Now, having to add up internal energy and flow work all the time is, well, it's a bit of a pain. So engineers, being the super efficient people they are, came up with the ultimate shortcut to deal with this.
So here's what they did. They looked at the two terms, the microscopic internal energy, U, and that flow work, PV, and they just bundled them together into one new super convenient property. They called it enthalpy, and they gave it the letter H. This just cleans up the math beautifully, so the total energy of our flowing stuff is now just its enthalpy plus its kinetic and potential energy. So much easier.
Okay, that's the theory. But how does this shortcut, this idea of enthalpy, actually help us build things? Let's take a look at where this stuff gets real.
Let's look at nozzles and diffusers. You find them all over jet engines. They're basically two sides of the same coin, and their whole job is to trade one type of energy for another. A nozzle makes a fluid go faster by converting its enthalpy, its internal heat and pressure, into raw speed, kinetic energy. A diffuser does the exact opposite. It slows the fluid down to turn that speed back into enthalpy, which jacks up the pressure.
It is the exact same story with turbines and compressors. A turbine is all about getting work out. Hot, high-pressure fluid rushes through. It expands, its enthalpy drops like a rock, and that lost energy is what spins the shaft to generate power. A compressor is the reverse. We put work in to spin it, which squeezes the fluid and raises its enthalpy.
And the kind of power we're talking about here is just staggering. A single typical steam turbine in a power plant can generate 5 megawatts of electricity. That can power thousands of homes, all from cashing in on that drop in the steam's enthalpy.
Now for something a little weird but super important, a throttling valve. It's just a simple restriction. When a fluid is forced through it, its pressure drops, sometimes a lot. But here's the crazy part. Its total enthalpy stays almost exactly the same. So if the pressure term drops, something else has to drop to keep the balance. And that's the temperature. This is the magic trick that makes your refrigerator and your air conditioner get cold.
All right, let's put this all together with one last kind of mind-bending example. We're going to look at an unsteady process, filling an empty tank. And this really shows you how powerful this whole energy accounting thing is.
So, here's the puzzle. You've got an empty tank, and it's insulated so no heat gets in or out. You open a valve and start filling it with steam from a pipe. The steam in the pipe is at 300 degrees Celsius. You let it fill up until the pressure inside matches the pipe, then you shut the valve. So, what's the final temperature of the steam that's now trapped inside the tank? Is it 300 degrees?
Get this. The answer is this shocking 456.1 degrees Celsius. Way, way hotter than the steam we put in. How is that even possible? It feels like we just broke physics, right?
Nope, not broken. We just saw the power of enthalpy firsthand. The answer is actually in this beautifully simple little equation. For this exact situation, the final internal energy of the steam inside the tank has to equal the enthalpy of the steam that flowed in. But why?
So where did all that extra heat come from? It came from the flow work. Remember that PV term we bundled into enthalpy? That was the energy used to push the steam into the tank. Well, once the steam was inside and stopped moving, that pushing energy had nowhere to go. So it converted directly into internal energy, which sent the temperature soaring. And that is how understanding the universe's accounting rules lets engineers predict and ultimately create the future.